last night about, we need like an optimization solver so that we can not have overlapping talks we want to see, because, we're going up against Fernando Perez in another talk that sounded really interesting, so thank you all for coming. This talk is up on GitHub, and I haven't got all the code that I'm showing up there yet, but I'm pushing that up today, so it should be up there later today if you go there later. Just a little bit about my background. This is kind of similar to Tyler's story. I worked at UCSB for 8 years, a branch of UCSB called NCS. It's an ecology center there, NSF funded. We worked on a lot of different kinds of problems. I mostly focus on spatial problems for ecologists. One of them was this map that I'm showing here, which is the global human uses of the ocean. So it's a global 1 kilometer square resolution data set that we put together based on 22 different threats and 17 different habitat types and a bunch of modeling to get us to this point of mapping human use of the oceans. So 2 years ago, I switched over to working for industry. NCS was an amazing place to work, but it was also soft money, and the uncertainty of knowing where your next paycheck was coming from was challenging at times. So I'm working for Dawn Wright, who's Esri's chief scientist, and she's an academic herself. She comes from Oregon State University, and she took over this job as chief scientist of Esri. And kind of one of her core goals is really trying to promote ocean science work within what Esri does. Historically, GIS has been very much focused on the terrestrial world. One of the things I like to say is that terrestrial folks get to cheat. They have $4 trillion of satellites, and they can image all of the globe. And those of us who work in the oceans can't directly remote sense our environment. So we have to rely on shipborne observations and do lots of other things to get data. We also have a much more complicated data domain because we have depth and time, and it's all in this kind of very coupled system. Some of the things that we are doing right now at Esri, Mark Janicus is here, and he works on some of these. We're doing a lot to really improve multidimensional support, starting to work on better support for vertical datum transformations. Things like Bayesian empirical kriging, so trying to have mixed models where you both have access to frequentist but also Bayesian tools. And I work on a few extensions that are built on top of ArcGIS, so they're open source, but they have a closed source dependency. They're tools for things like geomorphology operations and genetic analysis. And a lot of the stuff I do is really trying to help the GIS users who are scientific in nature kind of get what you guys all kind of know already, which is that, hey, GitHub's a good idea, and hey, we should do things like have unit tests so we can reproduce the results that we have. Those aren't common attributes for a lot of scientists still, and particularly if you look into GIS more broadly, so folks who are maybe working with the policy side or they're in government agencies, they don't yet have those tools in their toolbox. They're just kind of starting out with Python and moving away from purely being, kind of in a graphical environment into a more analytical role. So there's a lot of work to do to get them to kind of embrace the tooling that we really need for science to move forward. I just wanted to talk a little bit too about some of the background of GIS. A lot of it kind of comes from like this worldview of we had maps, right? We've been making maps for many thousands of years, but we realized that we have other data layers that we might want to display on top of the data that we've collected and do things synthetically across those. So, you can do this thing with acetate sheets, but you can only layer so many acetate sheets before you can no longer see the base map. So, some of the origin of this worldview, kind of Tomlinson and a lot of that early work came out of this idea, like, hey, we should just digitize all these things so that we can create these composite maps using machines instead of just doing it with pen and paper. So, getting a little bit more into the history of GIS, one of the things that's really interesting about the domain is that these tools got built up without necessarily good scientific understanding of how they get applied. So if you think about something like statistics, you have someone like Reverend Bayes walking around. Well, he had the idea about priors well before we had a Gibbs sampler. So the idea, a lot of those ideas have been around for a long time, and only recently have we had the computational power to actually be able to take advantage of them at scale. We could only really apply something like, Bayesian statistics for very narrow problems. And now computation has opened that up. So kind of the GIS history is a little bit inverted, where they had the tools and then they kind of afterward went back and said, hey, we need like a bunch of scientific methods to justify why we're doing these certain operations. And that creates some tension sometimes. And it's kind of interesting as well because a lot of the things we do, cartography, a lot of it has a very artistic component to it. So it's kind of this merged world of doing things that are really grounded in science, but also that are about appeasing the senses. These are just kind of a list of some of the primary things I think are what GIS is about. And I just wanted to mention this because I think it's useful to have a little more context about this domain, especially as we move into this really great space where we can do everything in Python, but maybe we still need to pull in some things from the historic GIS world. So one of the things I think is good, instructive to look at as well is what are the actual data representations that we have and use. And I think many of you are probably familiar with much of these, but most of the world breaks out into kind of a continuous fields representation, so some sort of raster structure. Usually that's in a very regularized grid, but it also can be things that are like things like finite element models and things that have some other structure that's not fixed. And then we also use lots of vector data, and primarily most people use non-planar, non-topological data sets, so things like shapefiles and GeoJSON and things of that nature. But there's also a whole bevy of tools for dealing with topologically validated vector data sets. And network, that should also say like graph structures, so that's a really important role for a lot of data ends up being really useful in that world, and obviously network theory has a lot of specific algorithms if you can get your data into that data structure. And then, we kind of have this like dimensionality thing where you have, different, you're really most of the time, if you're talking about actual existing implementations of GIS, we're like kind of somewhere between like there, like 2.5D, maybe sometimes 3D. There's not that many really robust implementations of true 4D objects yet, and that's kind of an emerging domain for GIS. And this picture here is just a map that Waldo Tobler made in the 60s, so it's kind of showing like we've been doing some of this stuff for quite a while. I did a survey of some of the scientific folks that I work with and kind of asked them like, well, what are the data models that you use for your stuff? And I think this is kind of instructive. Most people just use things like simple features, right? So like the OGC simple feature specification. That solves a lot of problems, and most people have that problem. And rasters and things like vectors with additional, Z or M values, those are pretty common. Point clouds gaining popularity. And then, some of the other things that we're really interested in, multidimensional data structures, this is partly a bias problem. The people I sampled for this are ocean science people, and they're not all, using NetCDF all day, every day. So, but still, I think this is a good representation of kind of the GIS worldview of what data structures they tend to use. And I also just wanted to throw in this quick tangent of, I think dealing with space is a lot like dealing with time. It's very simple to start out communicating about time, right? You can say, hey, meet me, I just moved to Boston, and this is a statue right in the downtown, in Boston Common. I don't know why, but it's a guy reading a book while writing a globe, and it says education under it. I don't know exactly. I need to learn about the history of this. But so I could tell you, like, meet me at 5 o'clock at the guy writing the globe. And we can easily do that, right? You could use the sun. You could use a number of methods for determining approximately 5 o'clock, and we could meet there, and it's no problem. But if you try to actually deal with time in a very robust way, you can't just use Unix epochs and get away with it, right? You have to actually start incorporating space. You need to know about where the time zones are. Those time zones change, and there's been actually copyright fights over people trying to say, no, like this information about where this boundary is for this time zone and when it applies to this place is my proprietary information. So you have to constantly be adjusting how you deal with the time zones. And you need very high resolution equipment if you want to measure that time precisely. So I think this is kind of how I like to see, some of the spatial domain. You can do a lot just by saying, meet me at 5 o'clock, but dealing with the full complexities of geographic space actually involves a lot of other things. So, it can get really hard and really difficult for scientific applications where we need precision and we need all these other things. Now that said, there's a lot you can do now just with, WGS84 and Web Mercator and you're kind of jettisoning all this stuff. But I think sometimes for scientific applications we need to retain some of that complexity still. I also want, there's a lot going on in the open source space, and it's really useful. I'm not going to go through too much of this right now, but I think one thing that's interesting for me is that there's a lot of hybrid solutions happening. So workflows now often involve many, 10, 12 tools easily, and so many of those components now might be open source, and we're really seeing a growth of pretty interesting interplay between those two realms that maybe historically are a little more divided. So just, why we are doing this GIS thing, I think, that we want to explore, we want to allow people to do spatial thinking and spatial problem solving, and not all those folks are computer scientists. They have tools that they know how to use now, and we want to educate them in where they should be going 5 or 10 years from now, but it's also important to meet them where they're at today. And, right now, desktop GIS is still broadly used. So, when I was at NCs, we had this same situation where we had to deploy tools to users who were using them in state government and other places, and whatever the back-end environment we used to compute that, it was really simple if we could make something that could be deployed into their ArcGIS environment. So kind of how I see things is that you have a GUI, so folks who are new, they can get accustomed to the GUI, try to provide a command line access to that and an API so that people who are getting more into a programmatic or batch processing worldview can do it. And the other thing I just wanted to mention is that while the web is growing really dramatically in this space, it still can't do everything. So latency is still a real problem. If you've ever used one of the DAC sites, you tell it like, hey, I want this data set. And they're like, great, we'll email you in 2 days when we've finished crunching it and getting it off tape. So if you have an analysis, often analytical processes take, many hours to run. And so there's still some challenges there getting that to run on the web, but that is changing over time. So why ArcGIS, beside the fact that they paid me Esri paid for me to come here? It's used in certain audiences pretty heavily. So for example, this is a survey of USGS folks. So about 65% of them use it, and it's their most commonly used analytical environment. But probably these numbers are changing over time, and clearly Python should, and I don't know, that seems way low for Python, that there's only 3% more Python people than MATLAB, but maybe that's true, I don't know. So ArcGIS has had Python for quite some time. It started about a decade ago. It's been incrementally improving. The core module that we ship with an installation of ArcGIS is called ArcPy, and that can probably run about 80% of what ArcGIS can do overall now. You can get to the rest with C types. And we're trying to continue building upon that and improving on that integration with the broader Python community. So right now, when someone gets ArcGIS, they get a Python installation, matplotlib, numpy, and then some things for Excel. NetCDF was just added recently, NetCDF for Python, and we're doing more to try to bring in even more pieces of the Python stack as much as we can, because one of the things we do is deal with all the installation hassles, which particularly on Windows is non-trivial. So if we can get more of the stack to our users, I think that'll be really of good mutual benefit to folks. What I work on a lot is these extensions, and historically these extensions had to be written in things like .NET, but just in the last few years they've been able to be written in Python. So that's kind of what I do most of the time, is I write these little Python wrappers that are executing Python code that then may use pure Python libraries or things from the Python ecosystem, but then also use things that are part of the ArcGIS ecosystem when that makes sense. So this is one that I work on here on the left. This is an add-in, so kind of you get a new menu in your inside of ArcGIS, and you can have buttons and tool palettes and a variety of relatively simple UI manifestations for how you might want to interact with that. And so for folks who are ArcGIS users, this is very familiar to them. And then on the right side is the Python toolbox, which is kind of the main way people chain together analytical processes in ArcGIS. So they have these idea of toolboxes, and then those individual tools can be strung together to form analyses, and that can be done without necessarily knowing how to directly program. So how that looks is, this is kind of a composite image of a one tool. If you open up a tool, this is what you would see, something like this. And so you have a number of values, and these things if you're interacting with this, you'd be picking, and it would filter the possible there'd be like a drop down here, so you could select data that's in the current map that you're working on, the map document. And then you have like contextualized help. And then this thing kind of in the lower right-hand corner, this is Model Builder, which is commonly used by ArcGIS folks to string together things. So those blue boxes are parameter inputs, and then the yellow boxes are individual processing steps. So they might use this to string together some analysis, and they can do this, it's kind of the proto-programming world. We're kind of trying to find some space between the actual writing of code and allowing people who want to make reproducible results possible. So with the more recent versions of ArcGIS, it's become much easier to deploy one of these things. Basically, it's just a Python script, a couple of Python scripts, one for the actual analytical things you want to do, and then one that's just laying out that UI you just saw. And then you can have a layout XML document. So if you need to say I have certain menus and these menus have icons, that's just an XML file. And when you do this, you get an installer. So a user would get something like this, and they can just click on install add-in, and it's pretty simple. You can do digital signing of those. And it's definitely an improvement over what was available in the past. So specifically, these Python toolboxes, basically you're creating a Python class, and you're for each tool you want to have in the toolbox. So in this example here, there's 8 tools. So that would be basically one Python class for the overall PYT, and then one additional Python class for each of those tools that I have inside of that toolbox. And I'll just walk through that in a second with an example, a simple example of how that works. And there's also this example that I'm about to show you is up on GitHub, though, like I mentioned, give me a couple hours before it's fully fleshed out. And then, as I mentioned, this add-in idea, there's just a simple set of things that you can add to one of these. They're relatively simplistic. They're not quite as sophisticated if you've used something like Tickle to make a UI or Tkinter. It's not to that level of UI specification, but it does allow you to do many of the common things that are useful. So, getting back to actual more science, one of the things that I help some of the scientists who use our software with is things like predictive species distribution modeling. So I actually work more primarily on this. If you have gridded environmental data, using things like geomorphometrics to try to extract more value out of data sets you might have, like bathymetry. But there's also this problem of actually running a predictive model. And this problem of species distribution modeling is very common in the ecological world. And there's a large variety of tools to deal with it. One of the problems is you have very biased sampling. You have very limited places where you actually have observations, and you usually have just presence absence at a time. You don't actually have some cohesive way of observing all the individuals at any given time. So this is really common, particularly with folks in the marine domain, because they're going out and doing things like, having someone look off the side of a ship and just taking the ship around on a certain track and then saying, this is how many whales we saw, and this is the sampling effort that we put toward that. And then the goal of this is trying to make probabilistic explanations of where we think these species live and where their habitat is. So this is a process that a lot of folks deal with. I'm going to speak about one that I don't really have any expertise in, so if someone knows more about this than me, then feel free to chip in. But one of the tools that folks use for this domain is called maximum entropy modeling, and it's basically a machine learning classifier that can be used for these kinds of problems. It's pretty robust to zero inflation problems, so it's really useful because of that sampling issue that I mentioned earlier. And the most common way that people do this right now in the ecology world is this Java tool here that basically you go to this guy at Princeton's website and you tell him yes, you will use it for good things, and then you download this jar file, and which is fine. It's great, but it does have a number of issues. The data has to be pre-processed to be in a certain format, and it has constraints on the naming conventions and things like that. So just for purposes of demonstration, I just threw together a quick toolbox that would show you what someone who might be an ArcGIS user could do to quickly wrap that, and that could then be shipped out and Okay, I'm wrapping up here. Okay, so I'm not going to go through the details of actually showing the code, but this is what that UI would look like, and I didn't want to get into the grid of the code, but that's the entire code that generates this UI you're looking at. It's just that little snippet there. So you can imagine then that down at the bottom it just runs an execute call, and you could do that without actually, so that execute call, then you're back into pure Python. The only thing you needed ArcPy for was just for generating this GUI and that one script. Okay, so that's it. Just wanted to quickly show you that, and I'm happy to, if you email me about questions about that, I'll show you more. But basically, I think it's really an interesting approach to make this shim so that you can share your tools with a much broader audience. And I think there are a number of folks who are using this where they might keep some of their work in core Python, but then they can get it out to this other new user audience. Great, thank you.